Vapor pressure and changes of state. Let's discuss what vapor pressure is. And we're going to start with a flask which has been closed off from the environment. And we're going to notice that if we have a liquid in that flask, the liquid is going to start to vaporize or evaporate. It's going to start to change from a liquid to a gas. But as gas starts to build up in that closed container, the vapor molecules are going to reform the liquid, or they're going to condense. And eventually we're going to get to the point where the rate of condensation equals the rate of evaporation in that closed container. And when we get to that point, we say that our system is at equilibrium. And equilibrium is established when there's no further net change that occurs in the amount of liquid or vapor in the container. And this is because the opposite processes exactly balance out, or the rate of evaporation equals the rate of condensation. Now when we look at a system that's at equilibrium, there's no net change from the macroscopic level. But if we were to look at the system at the molecular level, it's a very dynamic system. This means that the molecules are constantly escaping and re-entering the liquid. It's just that the net change is zero, or the amount of liquid on the bottom and the amount of vapor above the liquid becomes a constant at equilibrium. So if we wanted to graph this, if we looked at a system over time, and we compared the rate of evaporation to the rate of condensation. Initially, when all we have in the container is a liquid, we only have evaporation taking place. And since the temperature doesn't change for this particular system, the rate of evaporation stays the same. But as more and more gas forms above the liquid, the rate of condensation starts to go up. And when the rates of evaporation and the rate of condensation become equal, our system is at equilibrium. And the vapor pressure above the liquid becomes a constant. So our vapor pressures are determined by intermolecular forces. The larger the intermolecular forces, the lower the vapor pressure. And the reason for that is the molecules in a substance that have high intermolecular forces are going to need a lot more energy to escape than those that have lower intermolecular forces. So if a system has a high vapor pressure, it's because the liquid evaporates readily from that particular dish. And we say that the substance is a volatile substance. So let's look at vapor pressure measured in a barometer. And first we just want to review what a barometer is. So we've got this simple barometer. The purple is designating mercury. And we have a container of mercury which is open to the environment. And then we have an inverted tube which is sealed off at the top, which is filled with mercury as well. And when we invert that tube, the level of the mercury in that tube will establish itself at 760 torr if we're talking about standard pressure. So now what we're going to do is, instead of having a vacuum above that column of mercury, we're going to add some water. And that liquid water is going to start to evaporate until it establishes equilibrium. And as it evaporates, there's more gas above the mercury column pushing down on the mercury column. That's going to decrease the height of the mercury column. The difference between the original height and the new height is the vapor pressure of our water vapor above our mercury. So now let's change our system, and instead of having water above our column of mercury, we put ethanol. Now ethanol is going to change from a liquid to a gas until equilibrium is established. As the gas is produced, the pressure exerted on our column of mercury increases. And the difference between the original pressure at 760 and the new pressure gives us the vapor pressure of our ethanol. Now let's replace the ethanol with diethyl ether. And again, as that diethyl ether vaporizes, the gas above that column of mercury increases, the pressure exerted by that gas goes up, and the mercury level is forced down. The difference between the original 760 and the final pressure is the vapor pressure of our diethyl ether. Now, notice that water has a vapor pressure of 24 torr, ethanol has a pressure of 65 torr, and diethyl ether has a vapor pressure of 545 torr. The reason for that is water has higher intermolecular forces than ethanol or diethyl ether. So that means not as much of that liquid is going to become a vapor. Whereas diethyl ether has the weakest intermolecular forces, which means more of that liquid will change to a gas and increase the vapor pressure. So this shows us that intermolecular forces are related to vapor pressures. Now we want to talk about how temperature affects vapor pressures. And vapor pressure for a given liquid increases significantly with temperature. So we want to talk a little bit about why, and again we're going to graphically represent that. So what we have here are two figures that represent the distribution of molecular kinetic energy in a particular sample. So over on the left-hand side, we've got the distribution of molecular kinetic energy along the x-axis, and we've got the number of molecules with enough energy to overcome the intermolecular forces in the liquid and become a gas. If we notice, only a very small percentage of our molecules have enough energy to break the intermolecular forces and go from a liquid to a gas at a low temperature. But if we raise the temperature, the distribution of molecular energy changes. Now, at a higher temperature, more molecules are going to have enough energy to overcome the intermolecular forces and go from a liquid to a gas. So as temperature goes up, we have more molecules with enough kinetic energy to evaporate, and our vapor pressure increases. Now we've got a new graph. Here we're looking at vapor pressure as a function of temperature. And again, we're looking at the same three substances we looked at in our barometers earlier. We have diethyl ether, ethanol, and water. And we see that as the temperature goes up, the vapor pressure of those liquids increases. Now, at 760 torr, we get to what we define as our boiling point. And our boiling point is the temperature at which the vapor pressure of the liquid equals atmospheric pressure. Now, scientists, chemists, mathematicians, they don't like working with curves as much as they like working with straight lines. So if we were to take the natural log of our vapor pressure as a function of our inverse temperature, we end up with a straight line. And we can do some mathematical manipulations with a straight line. So let's again look at this natural log of the vapor pressure of our liquid as a function of the inverse temperature. And if we have a straight line, we can discuss slope, and we can make an equation for a straight line. So we know that y equals mx plus b is our equation for our straight line. And in this case, our y is our natural log of our vapor pressure. Our x is our inverse temperature, and c is a constant. The delta H of vaporization, or the enthalpy of vaporization, is the energy that's required for us to change 1 mole of a liquid to a gas, or to vaporize it. And we're going to divide it by our gas law constant. Now notice that we've got a negative sign in front of that value, and that's the reason because our slopes are negative slopes. We can evaluate the slope, and we can calculate what the enthalpy of vaporization is for a different liquid. And as we notice, since the slope for water is greater than our slope for our ethanol or our diethyl ether, it means that water has a greater intermolecular force than ethanol or diethyl ether, and therefore it's got a higher enthalpy of vaporization. Now, what if we have two temperatures? We can combine the two equations together at two different temperatures because C is a constant and it doesn't depend on what our temperature is. So what we're going to do is combine the two equations together since our C will be the same at two different temperatures. And we're going to manipulate the equation just a little bit using our natural logs. And we're going to get an equation that tells us that the natural log of the original vapor pressure minus the natural log of the final vapor pressure will equal our enthalpy of vaporization divided by our gas law constant times the inverse of temperature 2 minus the inverse of temperature 1. And if you know anything about natural log functions, we can manipulate this equation just a little bit more. And we could say the natural log of our initial vapor pressure divided by our final vapor pressure will give us, or is equal to, the enthalpy of vaporization divided by our gas law constant times the inverse temperature 2 minus the inverse temperature 1. We plug in the values we know, and we can solve for the value we don't know.